Hi, my name is Andrew Kadelka. In this presentation, our group will be presenting our Fall 2020 Computer Design and Analysis project, which will be focused on the optimization of an MLB legal wooden baseball bat. The issue we are trying to address with our project is the structural integrity of wooden bats. Wooden bats are far outpaced by their aluminum counterparts in terms of reliability. However, only wood is legal for use in MLB, as aluminum can propel baseballs at extreme speeds towards players on the field. Wooden bats, however, also present a different danger towards the batter in the form of wood shrapnel that can result from a shattered bat. A shattered bat usually occurs when a ball strikes the area between the handle and the barrel, known as the trademark. The desired impact spot on a bat is the barrel, the thicker end, as this area not only generates the greatest reaction force, but also can withstand the resultant vibrations of a hit. The trademark, however, is much thinner and cannot withstand those vibrations to the same degree. Our project will address this concern by seeking to reinforce this area. The desired improvements we plan to deliver with our project are as follows. Our bat must be able to withstand a baseball coming at 95 miles per hour. This speed represents the faster speeds that can be expected from MLB pitchers, with average speeds sitting around 92 miles per hour. We want our design to have a lower chance of shattering than current baseball bats. We also want our bat to be lighter, as lower weight correlates to a faster swing, which is an important factor when a pitch ball can reach the plate in less than a second. Also, our bat must follow the MLB standards, below 42 inches in length, no thicker than 2.61 inches, and a smooth, round surface. The material we'll be using for our bat is ashwood. Ashwood is the most popular bat type used in the MLB. This is due to the fact that ashwood is flexible in nature, which helps generate a greater reaction force when hitting a ball. This flexibility will also help in our design, as more rigid materials create a greater risk of shattering.
Hello, my name is Justin Chow, and I'll be talking about the next few slides, starting with the model. The model was first created in Creo and then moved into Abacus to implement the fillets. The length and barrel fitness were chosen to fit within the MLB standards that we found. The handle fitness was chosen at 1 inch to remain simple and not too much of an issue. The fillets and rounds we started at with a radius of 20 each. We felt that this was a good general number to start at, as it has room to increase and decrease. Next, we move on to design optimization. The thing we want to minimize for this project is the volume and weight of the bat. We want to stay close to the 33 ounce of an average bat to stay within the comfort zone of most players. We also want to optimize the fillet radius, as we expect the different radius effects to the volume and stress differently. Finally, we chose a max allowed stress at 120 psi, as we believe that this is a good middle ground stress for the bat to handle. Next are the three equations that are important for the project. The governing equation is the volume of the bat, which requires an integral due to the change in radius of the bat throughout its total length. The project only has two design variables, being the individual sizes of the fillets, which are then constrained at the previously mentioned 120 psi. When using the Excel sheet the professor had provided and demonstrated in class, we found that the stress of the bat could not be accurately approximated using a linear Taylor series. As such, we were forced to move on to a quadratic Taylor series. This was able to reduce the approximation error by a good deal for some combination of fillet radius, going from approximation errors of 25% down to 5%. Luckily, the volume was able to stay within a linear approximation and still maintain a low approximation error. Finally, we get to the MATLAB code. After some testing with the boundaries, we found that an upper radius of 100 was a good choice, as it doesn't take up too large of a portion of the bat, but is also still large enough to make significant differences. We chose 0 as a lower limit just in case one of the fillets was just unnecessary and would then be optimized out of the design by the program. We did have to do some fiddling around with the program to allow for quadratic Taylor series, but overall it remained very similar to what the professor had originally provided. The end results led to a 100 top fillet, maximizing its size, with a 44 bottom fillet to reach the maximum stress constraint. The volume was a bit higher than we would like, but still within the standards of MLB players.
My name is Sagar Patel, and I will be going through the Abacus portion of our project. So here are the boundary conditions and loading conditions for our simulation. The loading was done through a surface pressure force that was calculated using the contact area of a baseball and a bat, which we found through our research. The formula for the 95-mile-per-hour baseball is shown on the screen using contact time, velocity, and the mass. The boundary condition was created to depict a hand holding the bat during a swing. Therefore, it is not fully encastered because the hand still allows some degrees of freedom. We did not include the initial rotation of the bat, for which the reason we will discuss in our conclusion, but the force that we found was 1,284 psi, which was used on the surface that is shown by the red dot on the right image. So this is our original design. The volume was 100.31 inches cubed, and the stress on it came out to be about 185 psi. This is our optimized design with a total volume of 99.6 inches cubed, and this was simulated using the values we got from the MATLAB code, as the top fillet radii was supposed to be 100 and the bottom was 43.9222. We expected the top to be maxed out just as it did because we realized when increasing the fillet at the top, that led to the most volume loss on the entire bat. And this led to, for the simulation itself, 123.8 psi as the max stress. And we realized this was a little bit higher than what we saw in the MATLAB portion, as that calculated for 120. The main reason we believe the MATLAB optimization was lower than our Abacus simulation was mainly because in our Abacus simulation, we believe there could have been some shifting with our loads because the partitions could have been shifting when we changed the fillets for the top and the bottom at different values. And this could have also been the reason for our quadratic nature itself. As Justin mentioned, the error for the quadratic was much smaller than linear, even though we expected it to be a little bit more linear. We did not implement initial swing of the bat, mainly because when we tried to, it was skewing with the results in a way that was creating inconsistency. And just for the overall accuracy of our results, we believe that taking this portion out would be the best option. There are many benefits to the simulation. Safety is huge. Decreasing the stress of the bat leads to less pieces being able to fly off the bat when it gets hit with the baseball. Maybe it can hit someone like the catcher or something, so reducing that is obviously important. Preserving our swing speed by decreasing the volume and the weight itself is crucial for contact hitters in baseball. And just with less stress on the bat, one bat can be used a lot more often without worrying that it will break or it's worn down or something like that. And then finally, here we have our references, and these were used obviously to start us off on our project, generate our idea, and we got some crucial information from this, like the MLB standards of how the dimensions of a bat, and just tiny information that we needed were found in these references. So that is all for our presentation. So thank you for listening, and we hope you enjoyed.